So let's see if we can do code. All right, so here's right. So here, right, we know what the precondition is, we know what the postcondition is. We got to make sure that we hit the go to the end button. You know I hate that button. Oh, where are we? Merge sort. There we are. Look at all right. Don't hit that button. All right. So we're under the assumption that my friends are going to do what they're supposed to do, right? And now our job is to make sure that our routine works, right? They work for any input that's smaller than n, and I have to make mine to work for inputs of size n. All right, so what are we doing here, right? I think about my input, right? And right there's my input. And then I break my input into smaller inputs for my friends, right? So there are my smaller inputs for my friends. And then what do I do? Oh, it must be smaller, right? It's smaller. And it must meet the precondition, right? Everybody kind of agree with that? And then by magic, I get my friend to solve the problem, right? And so, how does it do it? Well, somehow here we're not going into how he does it. We're just saying it happens, right? And then their answers come back. And then what do? We solve our own problem, right? So here we take the two answers from our friends and we merge them together to get our answer, right? That's the merge part, right? Everybody see that? All right, and then this can't go forever. So if the input is so small that you can't give something smaller, then you have to solve it yourself, right? So if the input is of size 1, then it's just one guy, so it's already sorted. It's also nice to say if the input's of size 0, then it's already sorted, right? It's good to have those. My favorite base case is 0, but sometimes it's good to get 1 in there as well. Right? So that's what the base case does. Everybody kind of following that? And it's not Java. So your job will be to turn it into Java, right? I don't want to have to do that. It's painful. All right. Right. So this is just saying, I remember sitting with people who are coding and they don't know what they're doing, right? They barely read the question. They sit down and they type I equals 1. And I said, whoa, what's I? Why are you setting it to 1? Oh, code starts with that. Okay, but let's try to understand it first, right? Let's get it bigger. I mean, ChatGPT does 1 line at a time. So I don't know how he does it 1 line at a time, right? But right, I want to think about the algorithm more. And so you don't have to write the code in order, right? So I tend to do the high-level cases and not worry about the base case until later, right? How is this an algorithm? All right, that's a question, right? It's witchcraft. All right, so we want to write an algorithm, and we're assuming that it's already written in order to help us write it, right? You know that's silly. And I'll tell you the way I do run my life is if my key's locked in the house and I'm outside, I think, how can I get my key? Well, if I could get the door open, then I could go in and get the key, and then I could come out and I could open the door, right? Isn't that a good algorithm? Right? That's called. It's called the circular argument, right? If I could get the key, I could get the key. But the problem is you can't get the key, right? That's a circular argument, right? And so we have to break the circle, right? We can't. So what we do is we say, okay, my house is locked, but the key is not inside of my house. The key is inside of my neighbor's house. All right. Oh, but dear, my neighbor's house is also locked. Where's my neighbor's key? Well, it's in her neighbor's house, which is also locked. But the key's in her neighbor's house, right? So we keep doing this until the house is so small. Oh, one thing I didn't tell you is that we have a hierarchy of class here. I live in the most expensive house, right? It's big. And every neighbor's house is smaller. Or I'm just saying, all right? So the houses get smaller, right? And it gets so small so that the smallest house, right, we can just lift the roof off, brute force, we can solve it, right? And then you get the key and you can bubble back up, right? So that's what's really happening is we do this bubble down, and then we bubble back up, right? And when you have two friends, of course, it's more complex, right? Right, but this is the last time, we don't want to trace these things out, all right? All right, so let's talk about induction and strong induction, all right? So you've all taken 1019, so you're experts. And induction says, suppose we have a statement S that for every integer is either true or false, right? And every positive integer. And we want to prove that for all integers n greater or equal to 0, the statement's true, right? And how do we prove that? Well, there are an infinite number of integers, so you can't prove it for each of them. So instead, we prove it for 0, right? And then for every integer I, we prove that if it's true, we don't know it's true for I, but if it was true for I, then it would be true for I plus 1. Right? Everybody get that? In my other courses, I trace this out. Do we trace this out? No, we don't. Right, so what's happening? We proved it was true for 0, and because now we know it's true for 0, hence it's true for 1. And right now it's true for 1, hence it's true for 2. Right? Everybody kind of get that? Now I'm going to ask you a very deep philosophical question. Is induction true? Does it follow? Right? Well, our belief about the integers is that it's true, right? What do we believe about the integers? That if you go 0, 1, 2, 3, 4, and if you keep doing that forever, at no point will you reach all the integers, right? Because there's an infinite number of them. But for each integer, you will eventually get there, right? That's what we believe about integers. And induction is basically saying that, right? It says, if you start at 0 and you can always walk forward, you will eventually get everywhere. Yeah?
Like Hilbert's Grand Hotel, where if you're trying to pay infinite guests, you just move the guest in the very dimension.
Yeah, certainly infinities are very confusing, for sure. But I mean, I can imagine a different universe in which I have integers, and then there's this extra thing that's big and you never get to, right? And we have to, by saying, so that's why we call induction, this is not a truth, it's an axiom. We assume it to be true because it helps us define integers. In some ways, you could call this almost the definition of integers, is that you get, by counting, you get everywhere, right? All right, strong induction is, say you start by proving 0 again, and now for every integer I, I'm going to have, this is going to make my life easier, right? Because up there, I needed to prove SI plus 1, and all I had to help me was the previous one, right? But now I have to prove SI, and what I have to help is that some oracle, somebody is assuring me that all the previous ones work, right? If all the previous ones work, now I know lots and lots of stuff. I then have to prove that the next one's true, right? Does that make sense? And so in some ways, it's called strong induction. Well, because it's a stronger axiom. It's saying that induction works under this statement where I'm assuming more things, right? And you can see sort of why it works. Why? Because if you got 0, now I have everything before 1, so I can get 1. And now I have everything before 2, so I can get 2. Right? People get that? I know everything before 3, so I get 3. So people believe and understand induction, strong induction? Are we doing okay? Yeah?
By induction is also proved by strong induction? Because you can just be using less of it.
Yeah. I would say, why ever use induction at all, right? Because if you're allowed to do strong induction, if you've assumed everything previous, you only have to use the previous one, right? You can always convert it to an easier one, right? So if somebody gives you strong induction is true, there's no reason not to use it, right? All right. Maybe we do work it out. Right, so here, now we want to prove that our recursive program works, right? In fact, not only am I going to prove that merge sort works, I'm going to prove to you that every recursive program works, where what are our requirements? Our only requirements are, if you trust your friend, if you give your friend a smaller instance that meets the precondition, then by magic they solve it. And if the input's small enough, you solve it yourself. All right. So take any recursive program that does that, and we're going to now prove that that algorithm works. All right. So it's a meta proof. We're going to do it all at once. And what's the advantage of doing it all at once? Is you will never have to do it again, right? I've never put this on a test because it's sort of a meta proof, right? What we want is in your soul to join my cult religion, that all you have to do is trust your friends and life will be good, right? Once you believe that, then in the future you'll be fine, right? All right, so we need to prove that our recursive program, whichever program it is, works on every input of size n for every n, right? So we break that down into levels, right? And we make Sn the statement for all inputs of size n. My program works, right? It gives you the right answer. Everybody good with that? It's just a statement, and it's a statement that might be true and it might be false, right? And our goal is to prove that it's true, right? In fact, what is our goal? Our goal is to prove that for all n, S of n is true, right? If we prove all n, S of n is true, then we prove that all inputs of all sizes, our program gives you the right input, right output, right? So as soon as you want to say we're proving for all n, then it screams for induction, right? So what did we do? We wrote code that proves what's the base case? Well, the base case should work for inputs that are kind of small, right? So let's call that S of 0, inputs of size 0, 1, 2, 3, small inputs, right? The base case proves that the program works for small inputs, right? And then what do? And let's see, in fact, do we have more on the slides? Sometimes I chat and more here. Right? All right, so now what's this statement here? Well, you give me an arbitrary I, right? I want to prove for all I, so you give me an arbitrary I. And I then get to assume that S0 to Si minus 1 are true, right? My assumption is that the program works for any input that's smaller than I. Yeah?
Would that be a universal statement?
Yeah. For all inputs smaller than I, I'm assuming that it works, right? Do I know they work? No, I don't. I'm assuming it, right? We're proving this implication. So we're assuming it works for smaller inputs. And then I'm trying to prove that it works for inputs of size I, right? Now I need to prove that it works for all inputs of size I, right? So how do I do a for all proof? I say to my adversary, give me an arbitrary input of size I, right? Now I have an arbitrary input of size I. What does the code do? Well, it calls the routine on inputs that are smaller, right? But by magic, by our assumption, it works for those inputs that are smaller, right? And then my code, we know correctly, under the assumption that my friend gives me the right answer, combines them to get the right answer for my input, right? Does that make sense? Everybody see that when I say, assume by magic that your friends can give you the right answer as long as it meets the precondition and is smaller, right? That is what the left side of this implies is saying, right? And what we're doing is under the assumption that my friends work, I work as well, right? Does that make sense? Everybody get that? So then by strong induction, it works for all sizes, right? Everybody good? All right, any questions? Right, so if I was doing a logic course, which at 10 o'clock this morning I'm doing, now I would go more into the formal proof. I would talk about, well, no, I wouldn't do formal proofs. I'd do, adversary gives me something and I construct something and my oracle assures me of something, right? But here, I think this is enough to get you through the day, right? Everybody good with this? All right. So when I teach 3101, I start with a really strange multiplication algorithm to frighten them. Sometimes you start with an algorithm that frightens people so that they pay attention. Because if you make things too easy, they go to sleep. All right, so that one was too complicated to do, and I replaced it with a really stupid algorithm. All right, so this is stupid, right? Or maybe it's not stupid. Maybe it's just strange. All right. So what is it doing? Well, I'm claiming that it's multiplying, that it's taking X and Y and it's multiplying them, right? What is it actually doing? it's making X smaller by dividing it by 4. It's making Y smaller by multiplying it by 3. It's making X2 some weird thing. It's making Y the same as it was before, right? So that's weird. Oh, and then it recurses on these smaller guys, right? And then it adds those answers together. All right? Everybody agree that that's strange? Strange, right? Now, one would have to first argue, does the input get smaller, right? And here the X1 is getting smaller, but the Y is getting bigger, right? So you would have to have the measure of size be more influenced by X1. So the fact that X1 is getting smaller, in fact, maybe you could say the product of them. Why don't we have we can have any measure of size we want. So let's have our measure of size be the product. And you see, since we're dividing by 4 and multiplying by 3, the product is getting smaller, right? And in the second one, Y stays the same, but X is getting smaller. So, so the product is getting smaller, right? So we're giving our friends something smaller so we can trust that they work, right? Now, if you wanted to analyze the running time of this, we wouldn't, right? We wouldn't. Off the top of my head, I might say it's faster than the high school algorithm, but I wouldn't put money on it. All right, so what we want to do is prove that it works, right? So how do we prove it works, right? Well, our proof by induction, just like you did in 1019, right? By induction, we're going to assume that the statement S of n is the statement that it works for inputs of size n, right? And then for the base case, well, it works. It definitely works for all inputs smaller than 4, right? And why did I have so many base cases? Is probably to make sure we don't miss anything as we round down and do weird things, right? All right, so otherwise, what do our friends return this number and this number, and we return the sum, right? And by strong induction, oh, that's just plugging in our values that we did, and those are smaller. So by strong induction, our assumption, our friends' answers work, right? So we can just assume that the statement S of n is true for smaller things. So we assume our friends are multiplying. All right, everybody get that? And then there's not much else to say. You rearrange it and it works. Right? Everybody see that? And you've done, this looks strange, right? But I bet you in 1019 or in high school, you did prove some weird thing by induction that was almost as strange, right? I mean, this isn't so out of the, everybody buy this? All right. Oh, this is, I've said this already. You need to know what the precondition is so that you can know what you're going to get from your boss and you can give things to your boss. You need to know what's good for the postcondition so you can help the boss, right? But you also need to know what you're going to get from your friends, right? So it's really important to really clarify pre and post conditions. All right. And in fact, you know, when people code, they get bugs all the time, right? And I don't know if this is statistically true or not, but I would say that certainly as you're starting coding, the biggest source of bugs is you haven't defined the pre and post condition carefully enough, and we'll talk about loop invariants, right? You haven't defined the loop invariant. You haven't defined these contracts tight enough so that they meet up, right? Here, as I said already, maybe you want more from your friend or less from your friend, right? So for example, in merge sort, the input is I have an array and I'm trying to sort the numbers from 1 to n or from 0 to n minus 1, right? But I could loosen the requirement to say, if you want to sort from 100 to 110, that's good enough, right? Because we might need that, right? So that's loosening the pre and post conditions, right? Does that make sense? Everybody following? We're booting through this. Is anybody feeling lost? Excellent. Help.
Just on merge sort.
Yeah? Do you have a question about merge sort?
Yeah, so when you trust your friends to do it, you give one the smaller list and the other the bigger list, and then it gets merged together, and then you compare the last two values and those up by that.
Mhm.
Okay.
Yeah. Yeah. People kind of get merge sort, right? Any other thoughts? People feeling okay? We're whipping through this, right? I could slow down. Should we slow down? A little bit slower. All right. Tell me to breathe. Somebody, I've been a teacher for 30 years and I got my first present today, which was a box of chocolate from the last term student. And I ate 2 of them, which makes me more hyper. So there you have it. All right. So what are we doing? So you can change the pre and post condition, right? As long as you document it, right? And you have to handle any change you make, you also have to handle. All right. All right, good. All right. So we're going to go slower and we're going to understand stack frames. All right. I just gave you my whole religion about not micromanaging your friends. And what are we going to do now? We're going to micromanage our friends. All right. So somewhere in your brain, you should know what a recursive program actually does, right? And how it uses a stack. All right. So what is a stack frame? It's a block of when you start a routine up with a particular input, it's a stack of memory that routine is going to use, right? And for what does it need memory for? For all the local variables, it needs memory to store the value of them, right? It needs a program counter to say where in the code is it currently, right? That's what you need. So that's our stack frame up there, right? And we have one particular input. So we're ready to go, right? We got our stack frame, we got our input, we got a program counter, which tells us that we're on the first line, right? And so what do? We start executing it, right? Right, so we're gonna have different people because I still like different people. That's the yellow guy, and his job is to make sure this program runs, right? All right, so good. So, right, so this, I guess here we're still assuming that our friends work, but anyway, let's see what the slides say. All right, so what's the first thing I do? I check, is my input small? It's not, right? So what do? I construct the first half of my array, right? And there it is. Oh, so let me just say a little side here. So when I started at York, no, when I started as an undergrad in 82, what computers were doing was sorting, right? If you said, in the world, what is the most cycles spent doing? It was sorting. Why? Because computers were small and that's what they did, right? It took all their time just to sort. And so people were really big on sorting algorithms. And, we can teach you so many sorting algorithms historically, right? And what's the main difference between merge sort and quick sort is that merge sort can't be done in place, right? So what just happened there is we took our input, which was stored one place, and we copied it to another, half of it to another place, right? And that took too much memory and too much time. And that's why quicksort is better, because it doesn't do that. All right? Well, just a little historic side in case it interests you. All right? So we do the first half, right? And then our friend comes along, right? And our friend magically sorts it, right? And then what do I do? As I bring down the second half, right? And then my friend magically sorts it, right? And then, oh, look at that. I didn't catch what that picture was before. That's a little merger, right? Little red merger. So then it merges. I didn't make these slides, but 5 years ago. All right. So we merge them. Right? Does that make sense? That's my algorithm. Everybody buy that? All right. So, and then we return the answer. All right. So it still looks like magic. So we're going to do it again, right? How does my friend, now we're going to micromanage our friend, right? How does my friend solve the problem, right? My friend's going to have her own stack frame, right? And it's going to have its own local variables, right? And so when we called, oops, let's see. I hate these things up here. Go away. Right. So when we called our friend, right here, we're calling our friend. When you make a subroutine call, your stack frame kind of goes to sleep, and another stack frame of who you're calling goes on top, right? So your friend goes on top with her input, and what is she, right? Now you see it's the blue guy talking, right? The blue guy's worrying about this, and right, so the blue guy cuts the input in half, and right, then we could trust our friend, right? And so we go through it again, and that's how our friend works, right? And all right, but there's still a question, right? So now we can try to trace the whole thing out, right? Now we're going to have why they call stack frames is because you stack them up, right? So there's my input. I get my friend's input, and then I recursively call on my friend, right? We are sharing the screen, right? There's a question mark. I call my friend, right? So bang. Oh, when we move things, we have to click. All right, so I get paused, right? So what's happening to me? Well, my program counter, remember I have my own program counter. It's telling me that I'm on this line and I'm asleep. And when a prince comes and wakes me up, I will be alive again, ready to keep going, right? So I'm asleep, and now my friend's going, And are we running out of time? How much time we got? 5 minutes. Okay. 9 minutes. We can finish this, right? We were supposed to do that's not a unreasonable amount of recursion. All right. So then what happens? This guy, he cuts his input in half, right? And then he makes a recursive call, right? And then this person comes, right? She cuts her input in half, which is not quite half, but we don't worry about that. And she makes a recursive call, right? And then this guy cuts the list in half and makes a recursive call, right? And this guy says my own input's only of size 1, so it's sorted. And so they're done. So they return, and the answer returns back, and this guy's running again, right? Because we were on that line, we got the answer back, right? So then comes the other one, right, which is sorted. And then that's done. So we come back, and that's sorted, right? And then these two get merged together, right? Now this stack frame has the answer, so we return, and this has the answer. Are people kind of following this, right? And then we keep going, right? And this side we didn't have to go as far because it was only 1, right? And then we return, and then we merge, right? Now this guy's done, so her answer comes back, and we're ready to continue on. And I don't know how long I was willing to make slides. You know, I'm a bit of a slide making junkie, so who knows how long I did this, right? Are people kind of following this, right? And oh, look, we're going to go broke, right? And so on. Oh, there we go. Everybody get that? That's what really happens. All right. Now we have, right, so here's the tree of stack frames, right? So you can lay out the entire tree and think about it, right? But it's complicated, and and the only reason for doing this is when you need to compute the running time. You say, how much work does each of these individuals do, and you sum it up. But otherwise, you're better off with your friends. All right? Anybody have any questions about anything? Or you feel you kind of get recursion? All right? So let's do the following. When a recursive assignment comes, everybody try it, right? And if you get stuck, we'll come back here and we can see what we can do about it, right? Everybody good? I know I talked a little fast, but it helped to slow me down, all right? Have a good weekend. Yes. We are done with recursion today. We're going to go back to our previous scheduled stuff. And when we get to recursion, we'll jump to this slide. So let's remember where we are now. This was just to get you going for the assignment.
But on the introduction,
I think you were here. I would have noticed you.
no, I just registered yesterday.
Right.
Yeah. On the introduction slides, it says the assignments are posted, but I didn't see them.
All right. Let's go over what I know. The E-class, so there are 4 sections and we're sort of merged together. All right. So this is an E-class for the 4, and it will have, we're going to have, so common, each common says what we're doing in common. You should find my E-class contains nothing, right? Other than a link to this. And this, you should snoop around here. One thing, if you go into here and you say your name is York U, not my York U, then it would let you see last class's lecture, but I failed to get the pictures,
All of
right? So you might, but this is what I did last year, and this is what I did the year before. And no, that's not last. This is what I did 5 years ago. This is what I did the year, and it's probably the same. All right. And yeah,
It's just, on the introduction slides that you had posted, you said that over here, there should be another table with, the assignments.
oh, that's,
Yeah,
did I say that?
on the introduction slide. So I just wanted to confirm that I wasn't. missing
Oh,
something.
I lied to you then. Are these slides here?
Yeah, the first.
Yeah, we didn't cover them. So that's from before and we didn't cover them. Had Jackie not merged our courses together, I would have given you the same homework. But Jackie has volunteered he's the other professor, to do all the coding for us. So I removed this and we're gonna get it from Jackie. And what we're gonna get is 4 programming assignments that you do by yourself, but they're not worth anything. They're worth 5%. And then these programming tests. And yeah, so snoop around this page. If you have any questions, let me know. Welcome to our class. And you're great because you smile and make me happy. Yeah.
Thank you, sir.
All right. We're gonna have to leave here soon, I think. A class is coming. So let's do that. Let's get out of here.